Hi! Today we're going to be looking at how to calculate the transfer function of an RL circuit. Now, our circuit looks like this, and our transfer function, like in the case of the RC circuit, will be useful for us to be able to calculate the response of the circuit at many frequencies. So, if we recall from our previous RC circuit videos, we know that the transfer function is basically the output voltage over the input voltage when we see our circuit with its corresponding impedances. So in this case, we are going to use our j omega L as impedance, and we are going to keep our voltage divider, and basically our transfer function will be our output voltage over our input voltage. So the voltage divider will look like this. Output voltage is equal my input voltage times the impedance where I want to get my output, which is j omega L, over the sum of both impedances. So I have R plus j omega L. And with that, if I take the input voltage and bring it to the other side, I get the transfer function h of j omega equals output voltage over input voltage equals j omega L over R plus j omega L. Now we want to keep the j omega alone, so I'm going to bring the L out. J omega L over L times j omega plus R over L. And then this L goes with this L, and our transfer function is then j omega over j omega plus R over L. Now remember that when we get to this point, we have our transfer function here. It's important to see what the poles of our circuit are. Basically, the poles are the solutions or the roots of the denominator of the transfer function, which is sometimes called the characteristic equation. So the roots in this case will be R over L. It's one root because there's one. The differential equation that we got in one of the previous videos for this circuit was a first order differential equation because we have only one element that stores energy, and therefore here we also have a first order transfer function where we only have j omega. If we had for instance, in a circuit with one capacitor and one inductor, we would have here a term which is j omega squared. In this case, our highest order term for j omega is j omega, so we don't have j omega squared or j omega cubed, so it's a first order transfer function. And therefore we only have one root, which in this case is R over L. And if we remember before from our step response videos, we had that our time constant tau was L over R. So automatically makes R over L a frequency here. And that's going to be our special frequency that we're going to be talking about in the following videos. So the following videos, we will be looking at how to look at this transfer function at many frequencies so that we can figure out what response this circuit has. Thanks for watching.